In this video, we're going to do our first practice calculations involving work. So here's the scenario we're going to look at. We have a frictionless incline, which makes a 20-degree angle with the horizontal. We have a 5-kilogram mass, and the mass is going to be dragged up the incline by a string, which makes a 50-degree angle with the horizontal. The string has a 70 Newton tension, and it will drag the mass 8 meters along the incline. So this first part A here, is really a warm-up to prepare us to do the work calculation. So we're going to draw a figure over here, which shows the force diagram for the mass and also puts in the displacement vector. And then once we've done that, we're going to calculate the work done by each of the forces acting on the mass. So let's start with a force diagram. So I'm going to start by copying the mass off to the side here. Now, just out of habit, we can make our dashed line around the mass, and then we put in our forces. So first force would be the gravitational force, magnitude mg. And then, as usual, we can go around the dashed line and see where things are reaching in through the dashed line to touch the mass. So here we see the incline itself reaching in through the dashed line to touch the mass. Now, this is a frictionless incline, so the incline exerts only the normal force. And then we also have the tension in the string. Now, I want to represent the direction of that tension correctly. I'm going to go in here and indicate the direction of the incline. Now, the string here is held 50 degrees above the horizontal. The incline is 20 degrees above the horizontal, right? So if I start with the horizontal and then I go 20 degrees up to the incline, it must be another 30 degrees up to the direction of the string. That tension vector is making a 30-degree angle with the direction of the incline. And let's also put in the displacement vector. The displacement vector would be along the direction of the incline. Now, before we proceed to the calculation of work, I'd like to remind you of what we learned in the previous video regarding the sign of the work, whether it is positive, negative, or zero. So review this figure here from the previous video, and then look at the figure here and see if you can predict, without doing the calculation, whether the work done by each of those forces will be positive, negative, or zero. So in particular, look at the figure and see if you can figure out whether the work done by the gravitational force will be positive, negative, or zero, whether the work done by tension will be positive, negative, or zero, and whether the work done by the normal force will be positive, negative, or zero. So pause the video, think about these things, and then when you rejoin the video, we will talk about that together. Let's talk about the gravitational force first. Can you see that the angle between the gravitational force and the displacement vector is an obtuse angle, right? So between the gravitational force and the horizontal in here, that would be 90 degrees. But then to get up to the incline, we would add another 20 degrees. That puts us into an obtuse angle, and the work done in that case would be negative according to this figure. So the work done by the gravitational force would be negative. Now the angle between the tension force vector and the displacement is 30 degrees. That is an acute angle. So the work done by the tension force would be positive. Now, the normal force is perpendicular to the displacement. The work done by the normal force would be zero. Now, let's proceed with the calculations. Maybe I'll get this started by going through the calculation of work done by tension, and then maybe you'll try the other two on your own before rejoining the video. So work done by tension, I'm going to use the general formula for work over here. The work done by a force is the magnitude of the force. And in this case, that would be the magnitude of the tension force times the magnitude of the displacement and then times the cosine of the angle between the force vector and the displacement vector, in this case 30 degrees. So let's substitute. Magnitude of the tension force was given 70 newtons. Magnitude of the displacement also given 8 meters. And then we have cosine of 30 degrees. Upon substitution, I get 485. Well, remember, Newton meters is a joule. So 485 joules. Okay, so at this point, why don't you pause the video and try to calculate the work done by the normal force and the work done by the gravitational force on your own before rejoining the video. Okay, let's do the work done by the normal force together. Work done by the normal force would be equal to magnitude of the normal force times magnitude of the displacement times the cosine of the angle between the normal force vector and the displacement vector. Now, this is a 90-degree angle in here, so we have cosine 90. So the work done by the normal force is 0. Okay, one more to go. We want to calculate the work done by the gravitational force. Okay, so we have the work done by the gravitational force would be the magnitude of the gravitational force times the magnitude of the displacement times the cosine of the angle between them. So let's be careful about the angle between the gravitational force and the displacement. So I'm going to go back into here and indicate the horizontal. So the gravitational force is, of course, perpendicular to the horizontal. So this is a 90-degree angle in here. But then remember that from our figure, the angle between the horizontal and the incline is 20 degrees. So this is a 20-degree angle. So you can see then that the angle between the gravitational force vector and the displacement, 90 plus 20 is 110. So let's just keep going. The magnitude of the gravitational force is mg. Then we have magnitude of the displacement, cosine 110. The mass was given as 5 kilograms. Little g, as usual, 9.8 meters per second squared. Magnitude of the displacement, 8 meters. And we have cosine of 110. Okay, punching into my calculator, I get here minus 134. Let's look at the units. We have kilograms times meter squared over second squared. And if you recall from the previous video, kilograms times meter squared over second squared, that is another way of writing a joule. So we can say that the work done by the gravitational force is minus 134 joules. So now we've had a bit of an introduction to the idea of work. And in the next few videos, we're going to start to see just how powerful of an idea this is.